Okay, so we will continue with module 4. In today's lecture, we will try and look at two aspects. One is models for double layers, looking at Gouy Chapman theory, and hopefully if we have some time, we will also look at structure of electrical double layers. So, what we have done so far is to look at potential distribution near a planar charged surface. In that context, we have looked at solution of Poisson-Boltzmann equation. However, with a limitation that we are only considering the low potential case, which is what is called as a Debye-Huckel theory, in which we started off with one dimensional Poisson-Boltzmann equation, and then we showed that psi essentially goes as psi naught exponent minus kappa x, okay, where kappa is given by this particular expression. So, now what we want to do today is to essentially take out this limitation of low potential. That means, we would like to obtain a solution of the Poisson-Boltzmann equation without the low potential limitation. Okay, that is what we would like to do. Again, the starting expression is going to be one dimensional Poisson-Boltzmann equation, because we are assuming that psi varies only in the x direction. Okay, that is, we are only considering that psi is a function of x alone, and the solution for this particular case is given by what is called as a Gouy Chapman theory. So, for that we will again solve one dimensional Poisson-Boltzmann equation, and it turns out that for Z is to Z electrolyte, again the dependence of potential with separation distance is still going to be exponential, and is given by gamma is equal to gamma naught exponent minus kappa x, where gamma is exponent Z e psi by 2 kBt minus 1 divided by exponent Z e psi 2 kBt plus 1, and similarly gamma naught is same as, it takes the same similar functional form as gamma with psi replaced by psi naught. Okay, so, that is what we are going to derive in today's lecture. Again we will start with Poisson-Boltzmann equation, one dimensional case, and if you remember this, so we had d square psi by dx square is equal to minus rho star divided by epsilon. Instead of rho star, we have used the Boltzmann factor, and then we have written an expression for rho star, okay, which essentially is summation of for all the species that I have in the solution, I would have to sum up the contribution from all the ions that I have in the solution, okay, which is essentially is E times Zi times Ni, right, and with Ni being given by the Boltzmann factor. So, what we will do is we will start with this expression, and we will do some simple manipulation. So, we are going to multiply both the sides of this equation by 2 times d psi by dx. Okay, so, that is what we have on the left hand side, and that is what we have on the right hand side as well. Now, if you look at the left hand side, I can write this as d by dx of d psi by dx whole square. So, if I differentiate this function, so what I will get is, I get 2 times, that is 2 here, times d psi by dx multiplied by d square psi by dx square. Okay, so that is the left hand side term, and the right hand side term I can write this as d by dx of 2 times kBt divided by epsilon into sigma I Ni exponent of minus Zi e psi by kBt. So, if I differentiate this term, so the first term remains the same, kBt divided by epsilon, okay, and what you have here, so I am going to have sigma I Ni infinity, and if I am going to replace differentiate this term, is still going to be exponent minus Zi e psi by kBt multiplied by So, it is going to be multiplied by Z I E divided by KBT, right, and this KBT gets cancelled, right, and so therefore, and you have E here, right, that is the E there, and I have psi sorry epsilon. So, I have E by epsilon, and Z I is here, Z I N I infinity, that is this term, and of course, this term is as it is, okay, and of course, I have 2. So, essentially this by this simple manipulation I can write the one dimensional Poisson-Boltzmann equation as d by dx of d psi by dx whole square is equal to d by dx of 2 kBt divided by epsilon summation I n I infinity exponent of minus z I e psi divided by kBt. Okay, so now if I can integrate this expression, so I can integrate this on both the sides. So, what I'll be ending up with is d psi by dx whole square is equal to this plus a constant term. Okay, so we can evaluate the constant fairly easily. We know that psi is equal to 0 at x is equal to infinity, and d psi by dx therefore, because psi is equal to 0, you can also say that d psi by dx is equal to 0 at x is equal to infinity. So, if I substitute for these conditions, so this is 0, and if I substitute psi is equal to 0, this term becomes 1. Okay, therefore, essentially I have 2 kBt divided by epsilon summation I n I infinity, that is, and plus constant is equal to 0. Therefore, the constant essentially becomes minus 2 kBt divided by epsilon in summation I n I infinity. So, okay, so therefore, we have been able to evaluate the constant. I can substitute for the constant. So, therefore, I could write d psi by dx whole square as the first term minus the constant term, and because I have 2 kBt by epsilon summation I n I infinity as a common, I can take it out. Therefore, in the parenthesis I will have exponent minus z I e psi divided by kBt minus 1. Now, I can simplify now, because we are considering a specific case of Z is to Z electrolyte. What I can do is I can take this term, and then wherever whenever I have Z is to Z electrolyte, they are going to be Z plus and Z minus type of ions. Therefore, so because it's we are taking a symmetric electrolyte case, what I can do is I can wherever I have Z I can substitute for plus 1 as well as Z is equal to minus 1. So, that I account for both the co-ions and the counter ions in the solution. Therefore, the first term remains the same, and exponent of, if I substitute Z I as plus Z, right. Therefore, the first term is going to be exponent of minus Z e psi divided by kBt minus 1, and the next term, if I substitute for Z I to be minus Z, okay. So, therefore, the next term essentially becomes exponent of Z e psi divided by kBt. So, the substitution of Z is equal to plus 1, Z is equal to minus 1 is specifically for 1:1 electrolyte. Okay. If you have a 2:2 electrolyte, I would have to substitute Z is equal to plus 2 and Z is equal to minus 2, but because we are considering the case of a general Z is to Z electrolyte, therefore, it makes sense to replace Z I with minus Z I and Z I with plus Z I. Therefore, d psi by dx whole square essentially becomes 2 kBt n infinity divided by epsilon into exponent minus Z e psi divided by kBt minus 1 plus exponent Z e psi divided by kBt minus 1. The reason why we have taken n I infinity out of the summation sign is because for a given concentration n I for both plus Z and for minus Z ions is essentially the same, right. Therefore, I can actually take it out of the summation term. and it will become n infinity. Okay, so now that we have this, so what I can do is so this is what we had earlier, right? So there's minus 1 here and minus 1, that becomes minus 2, and in the parenthesis you have exponent of minus z e psi divided by kbt plus exponent of z e psi by kbt. If you look this up, you can write this as exponent minus z e psi divided by 2 kbt minus exponent z e psi divided by 2 kbt whole square. This is of the form a minus b whole square, which is same as a square plus b square minus 2ab. Therefore, I can recover this expression, right? So that I have the first term whole square, that is this, right. So I have so if you look at this expression, so I have exponent z e psi divided by 2 kbt whole square. Now I can simplify this. I can take the 2 in the numerator, this gets cancelled, so essentially I have the first term. Similarly, this that is this term. Similarly, so I have, again I can take the 2 in the numerator, so I can this gets cancelled, so essentially I have the first term here and the second term there. And if you look at this, this essentially is minus 2 times exponent minus z e psi divided by 2 kbt plus z e psi by 2 kbt. Essentially it is exponent of 0, which is 1. Therefore, I recover the minus 2. So therefore, so I can express this particular expression as d psi by dx whole square is 2 kbt n infinity divided by epsilon into exponent minus z e psi by 2 kbt minus exponent z e psi divided by 2 kbt whole square. Now again we are going to do some more manipulation. So we are going to assume, or we are going to put z as z e psi divided by kbt. This is a simple substitution. So therefore, from this what I get is I get psi to be y kbt divided by ze. So therefore, I can replace for psi in terms of y. So I have d by dx. Instead of psi, I am going to replace it with y kbt divided by ze, that is this term, multiplied by y, and the right hand side becomes 2 kbt n infinity by epsilon into exponent minus y by 2 minus exponent of y by 2, because we have substituted this to be y. Therefore, I have y here and I have 2 in the denominator. The same thing is also true for this case. So therefore, and because for a given electrolyte and a given temperature, kBt divided by Ze is constant, right? I am going to take kBt square divided by kBt divided by Ze whole square outside. So I have dy by dx whole square is equal to 2 kBt n infinity by epsilon multiplied by this term. That is, of course, which is valid only for a Z raised to Z electrolyte and at a given temperature, right. So, and what I can do is I can take the square root on both the sides of this expression. So, I will end up with dy by dx on the left hand side, and this term raised to the power 1.5, and this and the square root gets cancelled. I have exponent of minus y divided by 2 minus exponent of y divided by 2. Now, if you take a closer look at this expression, it turns out that you can relate that to the kappa. So, what we know from the definition of kappa is that kappa square is equal to E square divided by epsilon kBt multiplied by summation of I ni infinity into Zi square. Now, because we are considering Z is to Z electrolyte, I can write this as n infinity times plus Z whole square, okay, plus n infinity into minus Z whole square. Therefore, I will have 2 times Z square into ni infinity, that comes from the term in the parenthesis, and I have of course E square divided by epsilon kBt. Okay. So, now if you look at this expression and compare it to this, so what you essentially have is, if I take the square root on both sides, I have what I have is kappa is same as this term to the raised to the power of 1.5. Okay. So, therefore, so this particular expression which is valid for Z is to Z electrolyte, I can write it as dy by dx is equal to kappa times exponent of minus y by 2 minus exponent of y by 2. Now, I can separate the variables. So, I have dy, the terms with y on the one side, I can just rearrange this a bit. So, therefore, I end up with dy divided by exponent of minus y by 2 minus exponent minus y by 2 is equal to kappa times dx, and which if you want to evaluate this further, again we are going to substitute for y as e power y by 2. Therefore, dy by du by dy is e power y by 2 multiplied by 1.5, right. So, therefore, 2 times du, I can cross multiply them, 2 times du is e power y by 2 times dy. Therefore, dy essentially becomes 2 e power minus y by 2 into du. So, therefore, for dy we are going to substitute it as 2 times e power minus y by 2 into du, and this, because we have substituted so therefore, exponent of minus y by 2 minus exponent of y by 2, they remain the same. So, therefore, now what I can do is we could take this term to the denominator. Therefore, I have 2 dy multiplied by e power y by 2 multiplied by e power minus y by 2 minus e power y by 2. So, if I take e power y by 2 again in the inside the parenthesis, so I essentially have e power y by 2 minus y by 2 minus e power y by 2 plus y by 2. So, this becomes 1, and e power y by 2 plus y by 2 essentially is e power y itself. So, therefore, dy divided by exponent of minus y by 2 minus exponent y by 2 becomes 2 times du divided by it was actually 1 minus e power y, and because u is e power y by 2, essentially this becomes 1 minus u square, which I can write it as du divided by 1 plus u plus du divided by 1 minus u. So, therefore, if I simplify this, so it becomes du times 1 plus u plus 1 minus u divided by 1 minus u square. This gets cancelled. Essentially, you end up with what you had earlier. So, therefore, we've been able to simplify this. Okay, we have been able to recast this expression as du by 1 plus u plus du divided by 1 minus u is kappa times dx. So, I can integrate this easily. So, if I integrate this, what I essentially end up with is ln of 1 plus u minus ln of 1 minus u is equal to kappa x plus constant. Therefore, ln of 1 plus u divided by 1 minus u is equal to kappa times x plus constant. So, I can integrate again evaluate the constants. We have substituted u as e power y by 2, and therefore, y becomes z e psi divided by kBt, right. That is what we had done. So, if you go back, so it is u is equal to e power y by 2, and okay. So, therefore, we have substituted y to be z e psi divided by kBt. So, therefore, this comes from the substitution that we have done. Therefore, u essentially becomes e power instead of y, I am going to have z e psi divided by 2 by kBt, right, and of course, I have the 1 over 2 term there. Therefore, u becomes e power z e psi divided by 2 kBt. We know that at x is equal to 0, that means if I have a charged substrate and if this is how the x varies from the surface, at x is equal to 0, the potential is psi naught. Okay. So, if we have that, so now and therefore, at x is equal to 0, y naught becomes z e psi naught divided by kBt, and u naught becomes e power y naught divided by 2. So, we are essentially re-evaluating all the initial conditions and the boundary conditions in terms of y naught and u naught. So, therefore, if I substitute for x is equal to 0, so this term goes away, and what I end up with is the constant is equal to ln of 1 plus u naught divided by 1 minus u naught. Okay. So, therefore, we end up with ln of 1 plus u divided by 1 minus u is equal to kappa x plus ln of 1 plus u divided by 1 minus u. I can take this onto the other side, and if I again use the condition that ln of x minus ln of y is equal to ln of x by y. So, therefore, I have this term here, and because it is y divided by y. So, this it is, as you can notice, 1 minus u is in the numerator and 1 plus u is in the denominator. So, what we can do here is that I can, if you look at these terms, I can write this as minus of u naught minus 1. I can write this as minus of u minus 1. This gets cancelled. Therefore, what I end up with is 1 plus u or u plus 1, that remains as it is, and 1 plus u or u plus 1, that remains as it is, and 1 minus u I can write it as u naught minus 1, and 1 minus u I can write it as u minus 1. Okay. So, therefore, ln of u plus 1 divided by u naught minus 1 whole divided by u minus 1 multiplied by u naught plus 1 is kappa x. And so, of course, we would have to obtain an expression in terms of psi and psi naught, right. Therefore, we are going to again substitute back. So, because u is e power y by 2 and y is z e psi divided by kBt, I can write this u as e power y by 2 plus 1 times e power y naught by 2 minus 1 whole divided by. So, maybe let me just do a better job. Okay. So, I can substitute, I can write this as ln of e power y by 2 plus 1 multiplied by e power y naught by 2 minus 1 divided by e power y by 2 minus 1 times e power y naught by 2 minus 1, and because y is z e psi divided by kBt, I can substitute again for y here. So, essentially I end up with ln of exponent of z e psi divided by 2 kBt plus 1 times z e psi naught, because you have y naught here, I have z e psi naught divided by 2 kBt minus 1 whole divided by exponent of z e psi divided by 2 kBt minus 1, and that will be equal to kappa x. Okay. So, again some simple rearrangements. I can put together all the psi terms together and all the psi naught terms together. Therefore, gamma divided by gamma naught is exponent of minus kappa x. Therefore, gamma is equal to gamma naught exponent minus kappa x, where gamma and gamma naught are given by these expressions. So, therefore, we have been able to show, we have been able to obtain what is called as a Gouy Chapman theory, or a Gouy Chapman expression that was derived by Gouy and Chapman for how the potential varies with separation distance without limiting to the case of low potential. That means, this expression is valid for any situation except for the fact that we would still have to consider the symmetric Z is to Z type of electrolytes.